Welcome to Justin Math Calculus, Chapter 1, Limits and Derivatives, Section 1.1, Evaluating Limits. Let's start out by talking about what is a limit. The limit of a function f of x as x approaches some value a is the value that we would expect for f of a if we saw only the portion of the graph around but not including x equals a. For example, for the function f of x equals x squared, the limit as x approaches 2 is the same as the actual value of the function, which is 2 squared, or just 4. And this is pretty straightforward. Looking at the graph, as x approaches 2, it looks like the y value is going to go to 4, and indeed it does. But limits aren't always this straightforward. On the other hand, for the function f of x equals x squared if x is not equal to 2, and 1 if x is equal to 2, the limit as x approaches 2 is not the same as the actual value of the function. The limit is 4 while the actual value of the function is 1. In other words, based on the shape of the graph, the function looks like a parabola. And as x gets closer and closer to 2, the y value gets closer and closer to 4. So even though the function value is not actually 4 when the x is 2, we still say that the limit is 4 because that's where it looks like the function is going to go based on the surrounding parts of its graph. Even weirder, sometimes the limits don't even exist. For example, for the function f of x equals negative x minus 3 if x is less than or equal to 1, and x plus 4 if x is greater than negative 1, the limit comes out to different values depending on whether x approaches negative 1 from the left or the right. Approaching from the left, x is less than negative 1, so we're on the downward line negative x minus 3, and it looks like the function value is going to go to negative 2, so that's the limit from the left. But from the right, x is greater than negative 1, so we're on the upward line x plus 4, and that line looks like the y-coordinate is going to go to 3 when x goes to negative 1. So the right limit is 3. So it doesn't look like the graph is going to any single value as x approaches negative 1. It kind of depends whether we approach negative 1 from the left or the right. They come out to two different values, negative 2 and 3. In general, a limit exists when its left and right limits are equal, and does not exist if its left and right limits are not equal. For example, looking at the graph of 1 over x squared, as we approach 0 from the left, the function shoots up to infinity, and as we approach 0 from the right, the function also shoots up to infinity. So we say that the limit as x approaches 0 is just infinity, because both the left and right limits shoot up to infinity. But for the function 1 over x, the limit as x approaches 0 from the left shoots down to negative infinity, whereas the limit as x approaches 0 from the right shoots up to positive infinity, and these are two different values, therefore the limit does not exist. However, one exception to the rule that left and right limits must be equal is limits at infinity, meaning limits with x approaches infinity or x approaches negative infinity. In this case, it doesn't make sense to talk about a limit in more than one direction, because you can't find numbers greater than infinity or less than negative infinity. Limits at infinity can be thought of in terms of end behavior and horizontal asymptotes. For example, consider the polynomial negative x cubed plus x squared plus 5. The limit of this polynomial as x approaches infinity is just its end behavior as x approaches infinity, which consists of the polynomial shooting down to negative infinity. Likewise, the limit as x approaches negative infinity is just the end behavior of the polynomial as x approaches negative infinity, which consists of the polynomial shooting up to positive infinity. Here's another function, a rational function, r of x equals negative 2x over x plus 1, and the limit of r of x as x approaches infinity just consists of r of x settling down to the horizontal asymptote of negative 2. This is also what happens as x approaches negative infinity. The value of r of x approaches that horizontal asymptote negative 2. Lastly, here's an exponential function, f of x equals 2 to the x plus 3, and this function has mixed end behavior. As x approaches infinity, f of x also approaches infinity, but as x approaches negative infinity, f of x approaches 3. Some limits can be difficult to think about graphically, like this one below, limit as x approaches 0 of root 1 plus x minus 1 all over x. If we were to try to just plug in x equals 0 into this limit, then both the numerator and denominator would go to 0, and we'd have 0 over 0, which is indeterminate form. We can't really tell what it is just from the form 0 over 0. Thankfully though, algebraic tricks can often be used to simplify the limit to a point where we can plug in the value that x is approaching, in this case 0. We start off by multiplying the fraction inside the limit by the conjugate of the numerator. Then we can simplify that and cancel out a common factor, x, from the numerator and denominator, and we're left with a fraction where we can actually plug in the value x equals 0 into the fraction and get a sensible result. We do this and simplify, and we find out that the limit comes out to 1/2. Here's another example, the limit as x approaches negative 2 of x squared minus x minus 6 all over x plus 2. Again, if we plug in negative 2, we get 0 over 0, which is indeterminate. We can't really tell what the limit comes out to just from that form, but we can manipulate this limit a little bit. Let's factor the top into x plus 2 times x plus 3, and then we can cancel the x plus 2 on the top and the bottom, and we're just left with the limit of x minus 3, and now we can just plug in x equals negative 2. We get a result of negative 5. Another trick for evaluating limits is thinking about them numerically. Let's take that limit we just did. We already know it comes out to negative 5, but let's try to do this numerically. So we'll approximate the limit as x approaches negative 2 from the left by plugging in a number for x that is slightly smaller than negative 2. So a little bit to the left of negative 2, a little bit more negative than negative 2. So let's choose x equals negative 2.001, say. And when we plug that into the expression of the limit, we get a result of negative 5.001. We can do a similar thing to approximate the limit as x approaches negative 2 from the right. This time we'll choose a value for x that is slightly bigger than negative 2, a little bit more positive, say negative 1.999, and we'll plug that in, compute, and we get a result of negative 4.999. So based on those two values, we can reasonably infer that the limit is approaching negative 5. We'll also try this numerical process with the limit we did before that one, the limit of root 1 plus x minus 1 all over x. We already know this comes out to 1/2, but let's see how to do this numerically. First, we approximate the limit as x approaches 0 from the left. We plug in a value for x that is slightly smaller than 0, slightly more negative. How about x equals negative 0.001? We plug that in, compute, and the result is 0.5001. Likewise, to approximate the limit as x approaches 0 from the right, we choose a number for x that is slightly bigger than 0, slightly more positive. How about x is 0.001? And we plug that in, we compute, we get a result of 0.4999. So based on these two values, we can reasonably infer that the limit is approaching 0.5, or just a half.